Thank you, everyone. Thank you, Aishling, to come here to present your knowledge to us. So it's Aishling is coming from Chile, from La Serena, where she is a Noir Lab fellow, and she's going to talk about space situational awareness on satellites and space debris. Aishling got her PhD at the University of Kent and then moved to Astroscales in the UK when he studied the active debris removal in the system. So she's an expert and she's visiting for a few days.
Until tomorrow.
Until tomorrow. So if you have questions until tomorrow, you can ask. And you are in office. So you just
in an office. What's the number of it?
400.
400.
400. So it's upstairs for people interested in chatting. And I leave the stage. Thank you.
Perfect. Thank you. Right. There we go. Cool. So just a little bit of my background. The font might be small, but so my research is based on satellites and space debris, and also looking at the impact of all of that on astronomical observatories, but also seeing, can we use those observations in a useful way for like satellite operators or researchers, or if anyone wants to look at satellites in more detail, can you use the like astrophysics instruments to do it? So previously I worked at Astroscale, as was said, and that's a company that makes satellites to grab and deorbit dead satellites. And I was looking at different sensors and methods for on-orbit observations of other objects. And then I worked on hypervelocity impact experiments, my PhD. So I got to blow up loads of things. So that was fun. So this is kind of an introduction to the field of SSA. So has anyone ever heard of the term SSA before? No?
People cannot hear you.
Oh, people can't hear?
Oh, other people can.
Okay.
I think you can keep going.
Okay. Hello. You didn't miss much. But yeah, has anyone ever heard of SSA as a term? Right. So it's space situational awareness, and it just means, as I tell my mother, just being aware of situations in space. So just knowing what goes on, knowing where it is, knowing what it's doing. And then we have SDA, which is space domain awareness. So that's kind of the military kind of aspect to it. So instead of just characterizing objects, tracking objects, it's like the intent of those objects. So say if you have a satellite that has a telescope, it's where is that pointing at the Earth? So trying to figure out what way things point, what sort of instrumentation they might have is space domain awareness, but it's very similar. Space traffic management is to do with air traffic control in space, basically. And then resident space objects are what we call literally everything, just in orbit. So it's just an object in space. You don't have to define if it's man-made, if it's like naturally occurring, if it's big, if it's small. It's a resident space object. So then OD is orbital debris, but it's anthropogenic, which is the gender neutral term for man-made. That's used throughout SSA all the time. And then micrometeoroids are MM. So then MMOD is just everything that's really, really tiny, basically. And by tiny, I mean like smaller than about 10 centimeters in size.
What's this MMOD?
Micrometeoroids, orbital debris. So it's just the two mashed together, basically. Okay, and then we've got all the stakeholders in the like space domain. So you've got your astronomers, satellite operators, space agencies, you have industry, militaries, governments, policymakers, universities, and insurance companies as well. They care about space. They insure satellites. So how much space debris is out there? Does anyone have like an order of magnitude idea? Like thousands, tens of thousands, millions?
Well, you mean numbers of things bigger than what?
Just anything.
Oh, anything.
Yeah. But you can try, you can go bigger than like 1 meter is kind of like one chunk. And then 1 meter down to 10 centimeters is another chunk. 10 centimeters and smaller is like the small stuff.
Okay. 1 million bigger than a meter.
Okay. I have a little video that I'll show you.
I was about to get the same number.
Million? Yeah, so this is greater than 1 meter in size. So that's already thousands of objects. And usually if it's greater than 1 meter, it's operational, it's a big satellite. Then it's quite a slow video. But it changes, goes smaller and smaller in size. So you can like make out Geo kind of a bit, and most of Leo you can kind of see. I don't want to press buttons in case it breaks it.
So you use that term yesterday, LEO means low Earth orbit.
Low Earth orbit, yeah. And Geo's geosynchronous. So that's where all your television satellites would be, so that they're over the country, but also some spy satellites and stuff like that are there. So this is greater than 10 centimeters. So you can see like in low Earth orbit, it's getting a bit brighter, like more objects.
Which one is it? No, it's not that one.
And like the red ones are the functional ones, so you can only really make it out in Geo. Everything else is kind of random objects. And you can kind of make out the graveyard orbit as well in Geo. Very long, slow video. Okay, this is 1 centimeter now. So we're at like a couple million objects, roughly.
So at what level do we have situational awareness? Are they tracked?
Down to about 10 centimeters is trackable.
So
Mostly.
So this is basically down to a centimeter.
Yeah, so
How is that information?
spoilers for the rest of the presentation, but basically you have to do in orbit observations. So put something in orbit and let it get hit by objects. So then you can only statistically sample a certain area.
Oh,
So yeah, smaller than a millimeter, and that's all the objects. So there's an estimate, I think, I'm not good with remembering the number, but it's a couple 100 million, if not close to 1 billion, like objects in orbit. So yeah,
Quick question, I mean, there are some that are going like this, it's
Yeah.
zapping up and down. and this-
yeah,
there you go, there's one. Yeah,
Yeah, you've
it's
got-
so far out.
yeah.
elliptical orbits as
What's the
well.
point? Okay.
You've got the Molniya orbit as well. What other ones? Then there's ones from debris causing events as well.
So you're saying Earth has a ring?
Multiple rings, actually.
Wow.
Yeah. So that's just to give you some scale, basically, of what we're doing. Oh. Okay, so where did it come from is kind of the next question. So we've got major debris causing events. There's only been realistically 2 giant ones. So this was the first one. So it was a Chinese anti-satellite test. So it wasn't the first anti-satellite test in orbit. That was the US did that in the 70s or 50s. Sometime around that, I forget. But they tested it on their weather satellite. But the altitude, as you can see, is 800. And so when we talk about natural decay of objects, about 300 kilometers is like, it'll decay kind of quickly. Over 300 is kind of like, oh, that might take a bit longer. And about 500 is where you're like, oh, that's hundreds of years for it to decay. Sometimes depends on the shape of the object. But yeah, so it's at 800, so terrible choice on their part. So the debris cloud was the worst contamination in history. And also it's in a polar orbit, which is quite a popular orbit to use. So it's still there, all the debris. There's a good few objects still tracked, and they're going to be in orbit, the largest pieces, for about 250 years. And the largest pieces are like 10 centimeters or like around that. So not great. And then we have a collision between 2 satellites as well in 2009. So this was between Cosmos and Iridium satellite. So Cosmos was a defunct Russian satellite, and Iridium is part of a constellation. So the constellation, there's probably, at the time, I think there was about 70 satellites in the constellation, and they do little tiny maneuvers to keep their constellation intact, the shape of it the same. And then I forget what all these acronyms mean, but JSPOC used to operate some observations of satellites, but it wasn't public because it was a military operation. So they didn't have any of the operator maneuver plans, but Iridium was doing station keeping, so just staying in the same kind of area for its maintaining the constellation. And it did its maneuver 8 hours before the collision, which was faster than the update time of the military JSPOC catalog. So they didn't know in advance. And the only maneuverable object was Iridium. So they could have warned Iridium if they had a better system, if they had a more public system. So from that, they've kind of opened everything. Now everyone can kind of see most satellites on the systems. Sometimes they're hidden, sometimes they're just like anonymous on the system, but it's better for everyone that you don't crash into each other and leave giant debris clouds. So they're still here. So if you look at that video, you can see exactly these two locations. And because of the way it is, when it goes over the poles, the debris spreads all the way around. So it makes a giant cloud over everywhere, which is not great for anyone. So then this is the debris over time. So as you can see, kind of just jumps up here, and that's from the Fengyun 1C, and then it jumps up again from Cosmos Iridium. And you can see like about 2019 is when you have the launch of Starlink. And then lately you can see that like the payloads, which is the bright blue, kind of stay the same, which is kind of interesting because people are launching more and more, but the payloads on average are staying the same. So people are deorbiting a bit more. So it's looking kind of promising in some way, but the unidentified objects have increased a lot in the past year. So that's not good either. So it's a bit all over the place, but we have loads of objects, and these are only tracked objects as well. So doesn't include the tiny debris.
But before you go on.
Yeah.
Can you say what the other colours are? 'Cause I can barely read.
Oh yeah. Yeah, that's why I put it on the slide as well.
5, 7, Andrea, 2, 6, 5, 7.
So you've got the unidentified objects, so that's these ones here. And then you've got rocket mission related object, which is basically the parts that come off of a rocket. Then you've rocket debris, which is the dark red, which I don't really see much. Then rocket fragmentation debris, so when the rockets explode. So one of them exploded last year as well, so lots of the fragments from that. And two exploded in 2018 as well. So yeah, all those fragments are everywhere. And then you've got rocket bodies. So they kind of stay consistent because people have started realizing that it's not great to just leave a giant object in the way. So they've kind of just stopped doing that. Then you've got your payload mission related objects. So that's just your actual payloads maybe. And like parts that come off because of payloads as well. And then payload debris. So if it broke, payload fragmentation debris, if the payload blew up or if it got impacted and blew up. And then the payloads. So they're the dark colors. So yeah, lots of different chunks, but they're all kind of like mission related, rather than like actual small debris as well. So then the debris population, the tracking limits are about 10 centimeter in LEO and then about a meter in GEO, but this is kind of dependent on how much you want to pay for your tracking data. So if you pay a lot more, you can get down to smaller. And if you don't pay very much, the limit goes up. So in GEO, you might still get 30 meters rather than 1 meter. So depends on what you want to do. Small population is statistically inferred, as I said earlier. So it hasn't really been measured in the past 20 years realistically at a large scale. So we don't actually know if it's gotten bigger over the past 20 years, which it probably has, but no one wants to pay to measure it. And it's expensive to do because you have to put in orbit sensors. You might have to bring them back to Earth. So understandable, but also there's more traction at the moment for it. So then you've got lethal non-trackable debris is what you call something small that's not tracked, but can destroy a satellite. So that'll be something about a couple of centimeters in size. They say about like 2 centimeters is probably lethal, and then bigger as well. And this currently extends to the cislunar environment at the moment as well. They've found some debris. So then how do we track satellites and resident space objects? We have our system that we generally kind of use. So it's small stuff on the left, and then it gets bigger and bigger. So for the smaller stuff, we use return surfaces. So you've got stuff from Hubble, you've got stuff from the space shuttle, and it's just the outside of those surfaces and looking at what is there and the size of those objects. So it is still statistically inferring those objects. And also it's altitude dependent as well. It's only in the altitudes that they were in. So we don't actually know for the rest of space how much small stuff there is. And then when you get above about 2 millimeters, you can potentially measure it by radar if it's a charged object. And then when it's in low Earth orbit, you can use radar to measure up to about like, they use it for most objects actually. But then once you hit about 10 centimeters, you can do optical as well. And optical is used more for geo observations than LEO observations. And then we've got a little gap as well. So how do we measure the objects in that little gap that we've never measured before? So we look at the return surfaces. So I thought it'd be fun to show pictures of things that get impacted. So that's a Hubble solar panel. And then the image with the ball and the impact is just showing from a hypervelocity impact facility that a ball, I think it was like a couple of millimeters in size, did that to like a solid chunk of aluminium. And it's at hypervelocity, so the materials behave differently than if they're actually just normal velocity, I suppose. So it's that the compression wave travels much faster than the sound wave. So you get kind of odd behavior. Like you wouldn't get the little split off at the bottom there if it was just a normal speed, not at like 7 kilometers a second. And then you've got a returned airlock shield as well. So loads of tiny, tiny impacts. But from that, you can see the impacts or the statistics of what size objects are at that altitude. So then how do we know what part of the radio spectrum satellites use for communication so that we don't get interference for radio astronomy as well? So there's this thing where we just in my field call it spectrum, just as a broad term. It's the radio spectrum split up into all the little tiny chunks that people use it for. So you've got some maritime stuff, you've got some space stuff, you have communications, walkie-talkies, all that sort of stuff. And radio astronomy is on there in a tiny, the brightest yellow. So I've zoomed in on this one part, and then you can see the tiny, tiny radio astronomy part. So, yeah.
What does it mean that it's stacked up?
It means that you can do all of those in that one band. So you might get interference, but typically it means that they're across different zones. So the world is split into a couple of zones. And say you've got radio astronomy over here, you've got something else over here. They shouldn't interfere, realistically, but they're not too sure because this is managed by the International Telecommunications Union. So it's like part of the UN, basically. And they allocate parts of spectrum for satellite communications, but they don't really monitor it. So you could get allocated a huge wide band for your satellite, and you'd be like, woohoo, we got so much time, like so much space. But we're only going to use like the tiniest amount because we only have like a couple of satellites. We don't actually need to use the whole chunk that we've been allocated. So there's lots of parts that are allocated that aren't used, but no one gives it up. And then also no one monitors it. So if you have a teeny tiny chunk, but you're like, oh, but we need to go a tiny bit outside. Well, no one's really looking for it. So radio astronomers have started really looking into the kind of breaking the rules, not quite breaking the rules, but looking at who's using what spectrum and if people are going outside their bands or not even using their whole band. Because people are talking about renting out the whole band or like the extra parts or just giving it back or sharing, basically, because it is very crowded. So it's difficult to do like any new satellite constellations as well. So people just want to clear out all the leftover stuff at the moment so they can make new satellites. And yeah, and this is how as well we know the numbers of satellites that are coming, because when you submit like a satellite registration to your country, you're like, I want this many satellites. We're going to use this part of the radio spectrum. And then that has to be filed with ITU all the time, no matter what. So the ITU has all the filings. So if you want to see like however many satellites are coming, you can go on there and you can actually just have a look. You don't have to like do anything special. So that's why you see all the predictions of like hundreds of thousands of satellites. It's because they file for it just to get the spectrum allocation, but they mightn't actually use any of it because a lot of those companies go bankrupt before they actually build a satellite. So
Where is Starlink from this?
Starlink, they use
Just above, no?
Starlink would be just like these L-band. I don't know where L-band is on this giant thing, but yeah, it can be anywhere they've allocated like these fans. Forget where their one is though.
I'm sure this is a very dumb question. I assume a lot of these bans are for where you are allowed to emit.
Mhm.
What does radio astronomy emit?
I was gonna ask the same thing.
Oh.
Are there rules against listening?
No.
I mean, what is that? Does radio astronomy doesn't limit itself just to
Oh.
listening in that band, does it?
It's so that no one else emits in that band.
Yeah.
Is
So
the
it's a
thing
protected.
to protect it, yeah.
But they could opportunistically.
Yeah.
If they found there was a gap,
hmm
they could listen there as well. But
Yeah, at the moment, they found that the electronics on board of the satellites as well can emit in those bands.
Yeah.
So they're trying to figure that out because they need to find what exact bands that those are, and then tell people don't have your electronics emit at that band. But that's really weird to do because no one tests their electronics like that.
Yeah.
So everyone's kind of in a bit of a phase with that. So. But yeah, it's to protect radio astronomy, but there's a lot of disagreements about it. So they'll have like a meeting once a year, I think it is, and everyone gets together and shouts at each other and gets really intense, and they try to like get their own part of the spectrum that they want, and almost every time they ask for the radio astronomy parts, and the UN are
Not
like,
using it.
yeah. And they're like, it's so big. Like some of them are kind of big chunks for radio astronomy. So like that one is kind of big. But yeah, they're like, it's so big. And they don't do anything. They don't produce anything. They have no customers. What are they even doing? Is kind of their argument. And then the UN has to be like, you're not allowed. And they're like, come on, we can make money out of this. And it's like, it's difficult to argue for like the science case when it's like so many people just want to use it for like industrial activities. Yeah. So. But yeah, I found out from like the guys in Chile that no one had ever seen the radio spectrum thing. So I was like, that's nice to include. But yeah, so who decides what governs how we operate in space? So who decides when we do that sort of thing with the spectrum? So that was the UN and the ITU do that one. But we also have space policy. So these are the space treaties. There's 5 of them. They don't really do very much, but they kind of like set the tone of operations in space. So the reason why they're in quotation marks is because the names are really, really, really long. And this is just kind of how everyone refers to them rather than saying the giant names. So the outer space treaty is the biggest one, most important one. And it's the first one that kind of like tells you what's going on. And then they found that there were issues and things that they needed to fix. So they made all the next ones. So the rescue agreement is if you have a astronaut that's lost in space, everyone goes and rescues them. Or if you have an astronaut that lands in someone else's country, you can rescue them. That's fine. The liability convention is if you crash into my satellite, who's liable? No one really knows. The registration convention is so that everyone actually registers their satellites. So we know literally everything that's in space. Because if you just put loads of stuff up, and if you let all your citizens put loads of stuff up in space, how are you going to follow it? Who's going to be liable, like the previous convention? Because they realized you need to know who owns the things before you can be liable. And then there's the moon agreement, which is basically just don't colonize the moon. So in all these, there's 3 guiding principles is what they're called. So you've got cooperation, but they did not define it. You have mutual assistance, which it has its roots in maritime law and the law of the sea. So if someone's lost, go save them, basically. And then due regard is the biggest one throughout all the space treaties. And it's like operate in space with due regard for everyone else around you. But it's not explicitly defined. So no one really knows what it means. And you can kind of swing it whatever way you want. There's never really been a case that's gone all the way up to the International Court of Justice is where you can take all these. But once there is, then due regard will have to be defined. So everyone's just like preparing for it and waiting to see what happens. So then in the Outer Space Treaty, you've got kind of a set of principles. So it kind of just sets out how we want to operate in space. It's not really telling you Like, you're not allowed to do this, you're not allowed to do that. If you do this, then that happens. So it's for the exploration and use of space for the benefit of all humankind. So it's just kind of setting it out as a principle. So there's cooperation, and it kind of built on existing international law, kind of like the law of the sea, stuff to do with aerospace as well. So the other four treaties built on top of it when the gaps kind of showed themselves. And there's just, in the whole thing, it just says exploration and use without discrimination for the benefit of all. And they don't define what use is. And that's kind of a bit of an issue in terms of using resources in space. Are you like taking someone else's bit of space? Are you using up a resource? You know, that kind of thing. So that's where the due regard comes in as well. So it's kind of wishy-washy, but it is a treaty rather than like a set of laws realistically. So yeah. And then free access to all celestial bodies. So that's just basically don't colonize places in space. So then what drives the motivation to actually have space policy? Why would we even care? So there's space sustainability. So like to do with the climate and climate change, we want to have the long-term use of space for future generations. So whatever we do in space now, we want to make it so that everyone can continue using it and have the same opportunities, especially because there's some countries that are spacefaring nations and some that aren't. So you want to have those countries have an opportunity to actually get into space, use space, and like have the same advantages and resources that everyone else has. So we kind of want to clean up after ourselves in space, and it's beneficial for everybody because you minimize all the collisions and all the debris fields if you clean up after yourself. So that's the main incentive. There's no actual other incentive when you're talking about space sustainability. It's just you don't want to have to like sail your own satellite through your own debris cloud. So then the sustainability also extends to on-Earth activities like the satellite manufacturing and the launch, and then also in operations as well. But how can we be sustainable with some large defunct or dead satellites in orbit? So that's where we have active debris removal, where we try to remove them. And here's the major ideas at the moment. These were the main ones that people actually talk about. There's other weird ones like a space harpoon or like a space net or a bucket or like a really dense ball to like collect things through density. Yeah. But that would also just go out of control, I suppose. So no, great ideas. So these are the most reasonable ideas that people are actually building businesses around. So you've got the solar sail and the space tether are quite similar, where you have your mechanism that you have your own satellite, you fly over to the one that you want to deorbit, you stick something on it, and then you go away. So then the solar sail will deploy by itself, hopefully. And the tether one, still trying to get my head around this. So you just glue something onto the satellite, the tether comes out, it's about 30 meters long and about like this wide, so like maybe like 10 centimeters wide. So it increases your area to mass ratio, so you have more drag. So it should help you deorbit faster. So the goal of all these is deorbiting quickly. And that one no one likes, because if you leave a really, really long 30-meter wiggly thing, like how would you know if you're going to crash into it? So it's not great for collision avoidance. And then the more reasonable ones are a robotic arm. This company, ClearSpace, call their system tentacles. So yeah, to grab onto things. And then there's also magnets. So this was a satellite. This is from the company I used to work at. I used to get to play with this satellite and use the camera on it. But it was a demonstration of the magnetic docking system. So you can like pre-prepare a satellite that has a magnetic docking plate, and then you just dock together, change its orbit, and then undock, and it should hopefully deorbit faster. So that's the goal with the robotic arm one and the tentacles or the claw one, where you basically change the orbit so it deorbits quicker. No one's really actually done any of these yet. It's also an issue with dual use technologies. So you've got like military applications of these. If you went up to like a satellite and you wanted to deorbit and you just stick something on it and then run away, you know. But the goal of all of these technologies in like the commercial space is to do in space servicing and assembly. So basically, you have this technology of rendezvousing with an object. You grab the object and then you just recycle it. So you might move it to a recycling center and use it as raw materials, and then a new satellite pops out is kind of the goal. Or you might be able to take some materials from the satellites, especially stuff that's expensive or things that are hard to manufacture on Earth, but easy to manufacture in orbit, and then you can send it back to Earth. So those are kind of like the long-term goals of this sort of technology. But yeah. So then, oh, this is about, sorry, I forgot what I wrote. So last week I went to workshops and conference as well, and I'll be going to a conference next week. So I thought you might want to hear what happens at these sorts of conferences where there's a lot of industry and military people. So I went to a workshop for young professionals, and in my field, young professional is 18 to 35, 40. So most people, I suppose. And we started off with, because it was in Maui, we had a Hawaiian culture expert tell us all about voyaging, so that was fun. And then we had an innovation challenge where my team were working on the circular economy and in-space manufacturing. And then we had at the bottom here, this was a policy game, and this was really interesting. I thought I'd like tell you about this one because space policy is something you don't really hear much about. So this scenario was basically you had country A, B, and C. Then you had an SSA provider, so someone who tracks satellites and obtains data about satellites. And then we had two companies. We had country A had a company called Asteron. They all start with the letter of the country. It was so nice. So country A had Asteron, country B had Broadco, and country C had a weather satellite somewhere nearby. And the scenario was set up as Asteron went to refuel Broadco's satellite. So they went over, tried to refuel it, experienced some sort of event. So they decided to follow their abortion protocol. So they aborted the mission, and then they moved to a safe orbit. And then sometime later, a couple of hours later, a debris field was observed in the orbit of Broadco's satellite. And then country C had their weather satellite nearby, in a nearby orbit. So that's the scenario that we were set up with. But we all started off knowing nothing. So I was in country A, and we were like, I suppose let's go check on our company. We had no clue, nothing like that, anything had happened. So we walked over to their table. We were like, so, any news? And they were like, give us 1 second. And because we all knew the scenarios, then they discussed it amongst themselves, like, will we tell our country? Won't we tell our country? And we had the licensing agreement for the satellite, and they were like, doesn't say. We need to tell them. We don't need to tell them. We're not going to tell them. And they look up at us and they're like, we're not telling you. Everything's fine. It's all good. And we're like, oh, okay. Well, I suppose we have to keep pretending we know nothing. So then we went back to our table, and then country C came over and they were like, oh my God, how could you? And we were like, what? What did we do? And they were like, you made a debris field in like our area. And we were like, what? We have no idea. And then we were like, oh no, gosh. And then country B came over and they were like, oh, isn't that terrible how that mission went? And we were like, what happened? We had no idea. And so then we went to the SSA provider to get like some data so we could like see what happened. And they charged us $3 signs. And we were like, oh, very many dollar signs. So then we were like, oh, okay. And we signed country A. And then they were like, we can't tell you until after 24 hours. We're like, oh, we should have read the contract. So then that was the first round. And then the next round, we were talking to country C and they were like, you do know like something's happened with your satellite. And we were like, okay, let's go audit our space company. So we went over and we're like, we're doing a formal audit of you guys. And they were like, nothing's wrong. Because within their mission parameters, if they experience an anomaly, they just abort the mission and then go to a safe orbit. So they were like, we're good. And we were like, oh, damn it. And then the two countries kept coming being like, you need to do something. Your company is terrible. They made a debris cloud. And we were like, we don't know that they made it. Could have been like country B's company, like just their satellite exploded or something. It could have not been us. And then country B, they were like, well, our company wants compensation because they didn't get refueled. And we were like, oh no. So then we went through that, and this was run by Tahara, and she used to work at the National Space Council, advising at the White House on space policy. And so at the end of the game, because nothing really resolved. Basically, we just all got frustrated and we were like, we think our company is evil, and that was it. And she was like, yeah, this is how it goes in space policy, where like you try to come to a resolution, but then people come at you with like more information than you have, or better processes of communication with their companies or with other countries as well. Because country B and C were getting on great, and then we were like, oh, we're kind of alone, and all the countries hated us, but our company was evil. But in our licensing agreement, it didn't have teeth, as they say, so we couldn't enforce anything. So we were like, huh, well. So it was interesting to go through and see like what like the space policy kind of things is like. And then I had a presentation at the conference then. So it's the AMOS conference. So it stands for the Advanced Maui Optics Symposium, I think. I don't remember exactly. But my presentation was astronomical observatories as tools for space object characterization. So basically my presentation was saying that in SSA, what you want are these things. So basically all to do with your like satellite. So if you can get those from astronomical observatories, that would be fantastic, is kind of an SSA perspective. So you can see here, you can get most of those things, but not quite everything from just observations from telescopes that aren't targeted at satellites. So you can see like the orbital parameters and the distance and range are kind of the ones that are very iffy, but the material properties, maybe you can get timestamps. So yeah, that was kind of it, just showing people that you can use this data, but here's the considerations, and explaining that like you can't track an object in LEO realistically with large telescopes, or a lot of astronomy facilities don't do that as well. But you can do better quality observations than an all sky camera, which is what they typically use for tracking. So from that, the main aspects of interest from everyone in the audience over the course of the couple of days, they were asking about, could we do cislunar observations? Could we get spectra or multi-filter observations of different objects? Or could we get resolved imagery and light curves as well? Because light curves and resolved imagery are important for active debris removal, seeing if the object is tumbling. Also for anomalies, you might have a large satellite and has a deployable solar panel. Sometimes when you deploy, it might not come out all the way. So if you can make a resolved image, or as resolved as you can, you might be able to see that it didn't deploy. So they could figure out, oh, that's why it has no power, rather than it just didn't turn on. So yeah, if anyone is interested in solving these issues, or if anyone has any data on this sort of observations, feel free to hit me up, because this is what people are interested in as well. And then next week, I'm going to the IAC conference. So it's in Australia, and there's about 10,000 people show up. Yeah. It's really big. So
bigger than WES, right? Yeah, like 10 times, no? Yeah, yeah.
Three to four.
yeah.
Oh, yeah, it's like, yeah.
Yeah, the conference last week was about 1,500 people. So
How many?
1,500?
Oh, wow.
Yeah, my field that's small. So
Yeah,
doing a presentation to that many people.
oh,
But yeah, for this one, they parallel sessions, so it's like 4 or 5 at the same time. So the rooms are like 200-300 people rather than like a room of 10,000 people. That'd be crazy. But yeah, so you. But yeah, so you kind of like pick and choose the sessions. Sometimes they're on at the same time, and you're like, oh, no. But you can also like, because a lot of them are hybrid, so you can just like go to one session but have the other one on your phone and be like,
you need subtitles now.
yeah. But yeah, so the theme of this one is sustainable space, basically. So basically to do with removing objects from orbit, increasing sustainability in the practices on Earth as well. And they have sections on detection, tracking, environment modeling. So that's to do with the smaller debris, mitigation. So that's to do with like keeping your satellite intact and not making debris. Remediation. So if you made debris, what do you do about it? Sustainability and policy. And then I have a talk at this one, and it's almost the same as the other talk, but it's kind of more in a sustainability area, because there's sustainability policies, but sometimes they don't take into account sustainability in terms of astronomy. So they'll be like, deorbit your satellites within 5 years after the end of the mission, but they don't really think, oh, if you deorbit loads of stuff really, really quickly, it's kind of coming down and brighter. So not the best for astronomy realistically. So it's kind of looking into that sort of area. And then if you want to get involved with SSA sort of things, if anything piqued your interest, there's also the Center for the Protection of Dark and Quiet Skies. So Noir Lab's part of that. They raise an awareness for satellite interference. They measure the brightness of satellites as well. That's their main activity at the moment. And they make recommendations for policy. So like what sort of magnitudes should be the limiting magnitudes for the brightness of satellites. And then they work with industry on brightness mitigation. So different types of coatings they could have, different types of operations they could do. So point the solar panels away if they're going to be bright, that sort of thing. So yeah, I think, yeah, that's it. So thank you for listening, and I'm happy to take all of the questions.
Since
I have one question. Are you, so, well, I know some of the question because I like the answers because I talked to you yesterday, but you said that you were working with the NOAALab data, with a lot of data. Like also, like, are you including also Gemini data? Because I wasn't asking you yesterday that.
No, looking at DCAM data mostly at the moment. Yeah.
Would you be interested in checking?
Yeah.
I mean, I have some data with a lot of satellites on it. I can probably share it with you.
Satellites, basically. Yeah, that's what I did at the conference as well. I was like, everybody, send me the data. But yeah, no, if you have data with satellites, that'd be useful. Yeah.
If I get useful information on that, I would be happy.
you will ask 10,000 people.
No, yeah. I'm good at networking.
With camels.
Only usable data will
No.
actually become useful.
For her.
Yeah.
Like,
Yeah.
yeah, we
Wow.
have said like usable for Aishling.
Yeah.
Yeah.
Yeah, because most people are looking at the photometry of a streak as well, or looking at objects in geo as well. So they're not streaks really sometimes. So they're kind of difficult. But looking at things with different filters would be good as well. So that's why the like databases are useful. Even if it's just like one image, that's one filter. That's still adding to like the observations that we currently have of different objects. So yeah. Mhm.
So what type of information is there? Like what type of, when you have like the satellite in the image,
Yeah.
how do you extract the information?
Oh, depends. So at the moment, we're just trying to do the detection actually, like automatically,
Mhm.
because we're going through databases. So there's a group of us that are like, someone has a really nice machine learning algorithm for it. So we're trying to apply that to different databases. And then for the photometry, it's difficult because it depends on the orbit. So you have to like consider the angles as well. So it's a bit of an awkward one. But it's basically just similar to like just brightness over the whole length of the streak, basically. And then what else? Yeah, it's because it's annoying. Each observation is slightly different. So sometimes you'll have a streak and it'll just be like a straight line. Sometimes you'll have a streak and it'll have a couple of blobs. And you're like, okay. So you're like, is it rotating? And then you have to try and correlate it with what that object is and then see the structure of that. But sometimes people don't share the shapes of their satellites. And recently everyone's gotten annoyed about that. So that's nice because someone will do something about it. But yeah, so you have to kind of look at the average kind of satellite bus of like different orbits or different companies as well. You can message them, but they probably won't reply. But yeah, that's kind of like the main thing is kind of like figuring out what it was. So then you can do a better model because you could, if you wanted to, and if you had a lot of time, you can make a digital twin of the satellite and then rotate it and then simulate what the light curve would look like. But using data from astronomical observatories, because you only have one observation usually of each object. So why would you go through the whole process for one object when you have so many streaks? So it's kind of picking and choosing, basically, what to do with it.
Okay. Thank you.
Yeah, no worries.
Yeah, I have a question because I'm trying to connect some dots here. You said that there are many thousands of satellites bigger than 1 meter.
Yeah.
And when you go to the centimeter scale, work in the billion scale, you were saying.
Yeah.
So the small parts are not intentional. They were not things that were sent by us to
Mostly.
end there. Mostly. So
There's some small intentional stuff, but yeah.
malintention, I guess.
Interesting intention. There was one was they were in the Cold War, they were trying to have better communications, and because they didn't want the undersea cables to get cut, they wanted to reflect the radio off of clouds was kind of okay.
Yeah.
But they were like, what if we put a load of 1 foot long needles in space? Then we can reflect the radio off of that. So they released thousands. So they're still there.
It's still there.
Yeah.
Okay. Like looking for a needle in there. So the rest of the small parts are coming from incidents.
Yes. Yeah.
And do we have any knowledge of how many of those thousands of intentional satellites lead to the billions unintentional debris?
It's hard to track them, basically. So, like, a lot of it just comes from those 2 collisions that I showed, or
Yeah,
those 2 events. Like, that's most of the small debris is actually from those. And you've got some stuff from rocket bodies. They remove all the fuel when they're at the end of life, because they found that if you leave the fuel in it, because it sloshes about, it then explodes. So you have the fragmentation from the rocket bodies that exploded before we knew. And then you have all of the propellant that is like, it makes tiny aluminum oxide spheres. So they're like 100 microns in size, so they're small. And then they are just clumped together. And because they're kind of dense in comparison to like micrometeoroids are not very dense. But yeah, so they go around as well. So to try and track a lot of that sort of debris is almost impossible at this
These
point.
are byproducts more than an accident.
Yeah, because like even if you're going to geostationary orbit, like the fuel on the way is like when that comes out, that just floats around. So, you can't really remove it. It doesn't, like, it falls down eventually, but it doesn't really fall down. So, yeah, it's not great.
So you can just launch needles into space without asking others if they agree with that. Can I launch billions of nails in space and not ask anyone if that's okay?
Can, depending on the launching state. So that's kind of like how the law works. So if you're launching from the US, probably not. If you're launching from like New Zealand, maybe, who knows? You have to look at their licensing agreement. So like for one of our satellites in my last job, it went to inspect a rocket body, and then after it inspected the rocket body, it's just floating around, not really doing much, just deorbiting. But it had so many sensors and stuff on board. So with the UK licensed satellite we were like, oh, let's just take loads of random pictures of like random objects, mostly rocket bodies because they're big and bright. And then with that satellite, because it was licensed in Japan, because it's the Japan office, did it. And we were like, oh, can we use that after the mission to take pictures of random stuff because it has so many cameras? And you're not allowed to do that with Japan licensing for satellites, because you use it for what you put the main mission, what you put down as the main mission, and that's all you're allowed to do. You're not allowed to change mission after launch, after design, after the approval of the license. So it depends on the state.
If you still launch it tomorrow from your background, even from the US, do you go to prison for doing it?
What is this question?
Just bored.
What have you done?
Because you said that I'm planning. Because you said there's no law, right? There's just policy. So
Yeah. So you'd probably make the law then, actually. It would probably, so what would happen if you launch from the US, right? And you launch a whole load of random nails in orbit. Everyone else would then go to the US and be like, what's this? Why? Like, why did you license that? And then the US would be like, we didn't license that. So then everyone else would be like, well, because of the liability convention, they're liable. So then whatever happens with those nails, it's the US's fault. And then if it blows up other people's satellites, then the US has to pay compensation to them. But to figure out the compensation, you have to go to the International Court of Justice to actually do the whole process.
Well, I think in the US, we get into trouble before you even launch anything because it would track all your purchase for
Oh,
fuel.
Yeah, there are a
And
couple
it
of
catch you
obstacles,
before,
yeah.
Yeah.
Although
Right.
it brings a question we had when I was undergrad and sorry, grad school, grad student, we had too much time on our hands. And terrorism was the big fear at the time. And we were wondering how efficient it would be for someone to just do that, what you're describing, to just go mess up with satellites. And there are so many debris already. Adding 100 of them would not, or even 1,000 of them would not make. So there are movies that were based on the fact that debris hit something and then there's a chain reaction.
Yeah.
You're telling us there are millions of billions of them. So how come we're not having a chain reaction?
So the chain reaction is called Kessler syndrome, but you need a large enough initial object, basically initial population, to do that with. So at the moment, because the debris are so small, like the millions of debris are so small, and then the larger debris, they're well tracked and easily avoidable, mostly. So at the moment, it's fine because we have the space to avoid things. But if like one orbit is completely full, basically, and someone tries to go through it either direction, that's where you have a higher risk of doing something like that. And it would have to be in a very high trafficked or really, really densely populated area for that to happen. So at the moment, there's only really the constellation shells, and some of them aren't actually that dense. And they kind of take over a couple of shells realistically. So you can go through them without much issue. But if you launch all of the constellations that are planned, then you're going to have an issue. So it's basically you need to have a big enough impact in a really populated area to have that happen. So if Starlink malfunctions, basically, that's kind of it.
Can I ask a related one? So you said things like in the case of going and catching satellites, you were talking about nearby. What does nearby actually mean in low Earth orbit, for example?
So when you're doing active debris removal, it's kind of like you have your target objects before you launch. And the main limiting factor with satellites is just fuel, right? So you want to launch almost directly into the orbit that you want to be in, like the same orbit as your target object. And if you want to do multiple objects, you want them to be in the exact same orbits or like up or down, basically. But if they are, if the RAN is different, if you know what the RAN is, if they're like save the world and then it goes this way, if it goes that way is your other object, it's impossible to do it with fuel. You have to drift, and it might take a couple of years to do the drift. Yeah.
We're talking about tens of kilometers, hundreds of kilometers, thousands.
Oh, we're talking like for the altitude?
Yeah.
You can easily
Since
go.
I know it's up and down.
Yeah, you can easily go maybe like 100 or so without really being that concerned about your fuel consumption and design. But if you go like maybe 400, 500, that's where you have to build a bigger satellite just purely for the fuel. So
One last question. That was the question. I have one. Is LSST helping you or?
Oh, well, if we could get the data, that would be helpful. Yeah. If they don't remove all the streaks. If we can get the data with the streaks, that would be handy.
Well, they could give you the streak.
Yeah.
Out of the data.
All we want is just the streaks, actually. We don't.
She's the opposite of astronomers. No, I don't want them. You are, yes, give it to me.
Just the streaks. That's all we want.
You should be involved in all the data processing because you know what you wanted, right? And you take it for your
Exactly,
science.
just like, you know,
Yeah.
But yeah, no, it would be useful though. Like at the conference last week, everyone was asking me about it as well. Being like, oh my gosh, can we just use the data? That'll be so useful. And I was like, well, it won't be the most useful because what people really want is tracking data but the orbits, the uncertainties are quite large. So the data kind of expires after about 8 hours. So if you can't release the images, process them and have the data within 8 hours, it's useless.
Wow. Wow.
But they can detect supernovae in a minute.
Yeah, but the issue is kind of like security.
Oh,
So if you're like tracking all these satellites and then releasing all the data publicly, that is,
I heard that was an issue with Pan-STARRS, probably,
yeah,
right? That they didn't want to release the data or something because they needed to like wait a certain amount of time in
Yeah.
order
They
not to.
cut away the parts, so it's
Yeah,
like
something
very
like
much
that.
with like alignment, you
Yeah,
know.
yeah.
Yeah, I was like, I want that.
Yeah, they were saying that they have to wait 80 hours from like taking the data to releasing it if it has a satellite, just so that it's like decayed.
Yeah. Yes, it's-
Well, it's useful in other ways, not for tracking, but for like object characterization. So you can do that. So like last week when I was talking to people and they're all asking like, could you do something useful for us? I'm like, it won't be fast, but yes. So that's kind of like what you can offer if you meet a satellite person.
Okay. Thank you very much, everyone. Thank Aishling again.
Yeah, thank you.